The multinomial logistics regression. The multinomial logistic regression procedure permits the estimation of a model with a polycotomous or multi-category dependent variable. Specifically, the dependent variable may have more than two categories. Now, we're talking here categories, which means the dependent variable doesn't have ranked or hierarchical values. It's as if you have categories that are equal or equivalent and not rankable, such as different cities, or a choice between more than two political parties. So first we're going to retrieve the data, and the data is titled the application, the multinomial logistic data set, which we open. It's a multivariate model. There are three independent variables, and so the model basically predicts that income in crores of rupees, gender divided as male-female, and age in years is regressed against the political party choice. In this case of Pakistan, you have JI, Jamiat Islamiyah, PPP, which is the People's Party of Pakistan, and the PML, which is the Pakistan Muslim League. So all of the usual preliminary diagnostics apply for logistic regression, including testing for skewness and kurtosis, for normality in the independent variables, multicollinearity, which is set at 0.5 of a correlation because this is a logistic regression, and 3, the identification exclusion of extreme outliers, beyond 3 standard deviations. So the basic logic of the multinomial logistic is that it's a statistical procedure which takes the lowest frequency category in the dependent variable and then uses it as a reference category. And this you're going to see as a recurring technique for a lot of the techniques that use nominal or categorical variables. It's not going to report all of the different categories. It's not going to report the values for all three parties. It's going to report the values for the more frequent parties and leave one of those categories as the reference category, and it's going to give it no values. So the values are going to be a ratio, a complex ratio. It's not directly comparable between the reference categories and the other categories. So let's go ahead and run the multinomial logistic regression procedure. Step 1 is to go to Analyze, Regression, Multinomial Logistic. We open that up. The dependent variable is party. Factors are categorical variables like gender in this case. The covariates are the independent variables that are continuous like age and income. Now, in addition to the normal default characteristics that would be used, such as the QQ plot for diagnostics after you've run the regression, in addition to that, we have some other statistics that need to be run. We're going to click on cell probabilities, classification plots, and goodness of fit. Click continue and then click OK. So these are the results. Let's start here with, at the very top, the model fitting information. So the final row, and which here at the bottom right you can see has a significance of 0.00, provides a diagnostic test of whether the addition of the independent variables into the model provides explanatory improvement of the model with just the intercept and no independent variables. So you think about it, we have here 3 categories of political parties, and we have a frequency of how many people are broken up into those 3 political parties. We could just, if one of the political parties has 67% of the respondents associated with that party, we would just guess for every single individual, we would simply guess that they're a part of that one party, because we have a 67% chance of getting it right. So what this does is it compares that 67% to the predictive power of all of the independent variables included in the model. And you're going to see later on, by including the independent variables, we actually are making perfect predictions, which is an improvement from 67% to 100%, which is a 33% rather improvement. So the significance of a probability of less than 0.05 indicates a low probability of a false positive. Now here it looks like an F statistic because it looks at the entire model, but what we're actually doing here is a chi-square. So let's go now next to the goodness of fit, the next diagnostic. This is the Pearson chi-square correlational statistic. Now here we have to be very careful. Pearson chi-squares that will occur more and more frequently when we're using categorical variables are interpreted in the opposite fashion of a normal significance test, and even in the opposite fashion of a typical chi-square statistic significance test. If there is a significant result, and here let's look at the significance is 1.00. This would be traditionally not a significant result, right? Because we would normally want a value of less than 0.05, less than 5%. But if there's a significant result, it indicates that the model does not fit the data well. A significance of less than 0.05 indicates that the model does not fit the data well here. So a low chi-square value approaching 0 and a high significance value approaching 1 indicates a good fit for the model, which is here meaning we have a good fit. Low chi-square, high significance means a good fit. Now in the last line we have the deviance chi-square, and it's a variation of the Pearson chi-square, and the diagnostic is judged in a similar way. So both of these indicate that we have a good correlational statistic. So here we've got the pseudo R-squares. The R-squared is an analog of the linear regression R-squared, which measures the proportion of the variance in the dependent variable explained by the independent variables, but is nonetheless constructed differently and should be interpreted with caution. Cox and Snell, Nagelkerke, and McFadden are three typical pseudo R-square values. So let's go now to the likelihood ratio test. Now this table is primarily for assessing the contribution of nominal level independent variables, including dummy variables, but the significance test results apply to all of the independent variables. So of course we use gender. The significance of the independent variables at the probability of 0.05 indicates that the variable's effects on the dependent variable is not a false positive. So in the example we used gender, and it's not significant, as we can see. Got a significance of 1.0. Income variables are better dealt with by parameter estimates table, which we're going to look at next, as well as the age variable. So although age and income are significant, this is not a profound test because it's primarily designed for categorical variables, and gender is not a variable that either improves predictions or significantly predicts the outcome in the dependent variable. All right, so here we have the parameter estimates on top. There's one section for each of the categories after the first in the dependent variable. So in the example, there are three categories for party: Pakistan Muslim League, Pakistan Party, People's Party of Pakistan, and Jamiat Islamiyah. And two of the categories are retained: Jamiat Islamiyah and the Pakistan Muslim League. Statistics are reported for each of these categories in the dependent variable. So the excluded category of the dependent variable is called the reference category, which in this case is the People's Party of Pakistan. And the reported statistics are in comparison to this category. Now the nominal level variable, which in this case is gender, and you can see gender F and gender M, has no values reported for one of the categories, which is set as the baseline. And the other category has the diagnostics, which in this case is the female category. Each variable has a B coefficient and a standard error, which is used to calculate the Wald statistic. And that in turn is used to calculate the significance test, which occurs here in the middle column. None of the example variables are significant. We are not able to generalize that from the sample to the population, and we're also not able to probabilistically be certain enough that these relationships are not false positive. The exponent B, which is in the third category from the right, which is the exponential value of the B coefficient, is more interpretable in a multinomial regression than the B coefficient, and is therefore used instead, typically. So here we have the classification plot. The classification plot indicates how well the model is at predicting party affiliation. Observed means what's actually existing in nature. Predicted is what the model predicts. So we obviously prefer the prediction to be as close as possible to the actual or observed distribution of cases, or distribution of cases in the different categories. So in this instance, the model's ability to predict is perfect. I mean, we have Jamida Zalimi has got 65 cases. We predicted all 65 cases. Pakistan Muslim League has 65 cases. We predicted all the cases. And the People's Party of Pakistan, the smallest category, we predicted 100% of the cases. So the overall percentage, 100%. This is a 34% improvement over the prediction made simply on the categories of the independent variables. So this is a good model, even if it's not generalizable. And finally, the last table is the observed and predicted frequencies. The variables of income, age, gender, and party are cross-tabulated and used to examine the prediction rates of the independent variables on the categories of the dependent variables. So again, we have the column of observed and predicted, and it tells us what the observed value, actual value is, and then what the predicted value is. Now we're going to get perfect scores on this table. And you can just take it all the way down for every category. So it shows us how well we are able to predict. The one thing I have not shown you, simply because I haven't found it, is how to create a prediction equation, which I predict is going to be especially complex with a multinomial logistic. But there isn't an obvious way to calculate it.